find the moment of inertia of a solid hemisphere about this diameter. So this is solid hemisphere. You have seen that is whether when we are talking about a cylinder, which is solid cylinder, what we have done is we have taken at a distance x, we have taken a small section at a distance x, we have taken a small section dx. So this makes a disk. So this makes a disk. So how had been our approach? We had found the moment of inertia of this disk, a general disk, which is at distance x, thickness dx. We had found the moment of inertia about this, that is ICM. Then we have found the moment of inertia of this disk about this axis using parallax theorem, that is ICM plus dm. Let's say if we call the mass of this as dm into x square, we have used this to find the moment of inertia about, if we call this as yy dash axis. So Iyy dash axis had been integral of this, right? Then we had done in cone also. When we had taken the cone, once again at a distance x, we have taken a small disk of thickness dx. Over here it was all linear, uniform. So we have used mass per unit length. But over here, that is as the y is changing, so this is, we cannot say that is mass per unit length is constant. Then over there we have used the relation, that is y by x is equal to r by h, that is y by x is equal to r by h, where y and x, though both of them they are the variables, but they are not independent variables, they are interdependent. Then what we have done is we have changed one variable into other, that is how y is equal to r by h into x. So then finally we get ICM in terms of x only. Then once again we use parallax theorem, we find the moment of inertia of this general disk about this axis, and then we integrate x from 0 to x is equal to h, and we get the answer. Thus once again we have to use the same approach in finding the moment of inertia of this hemisphere, solid hemisphere, about this diameter. So what we do is, that is at a distance x, we take this small section which makes, obviously at a distance x we have taken a small section of dx, which is obviously that makes once again a disk only. This makes a disk only, which has suppose diameter is, radius is y and thickness is dx. Approach remains same. Once again we'll find the moment of inertia of this disk about this axis, that is ICM. We'll find ICM, and this will be, obviously we know that is if the disk is there, moment of inertia we know that is about this axis mr square by 2, about this and this axis, if about this axis I, about this axis I, and both of them are perpendicular, we have used the perpendicular theorem, and we have said I plus I, 2I is equal to mr square by 2, that is Izz is mr square by 2. So I about any diameter is mr square by 4. So we had used this concept to find ICM, that is dm into over here, suppose it y, that is m into r square by 4, this we get ICM. Then we use the parallax theorem, that is Iyy dash is equal to ICM plus dm into x square, we'll use it, and then we'll integrate. If there are two variables y and x, then what we do, in case we intend to integrate from 0 to r, then we'll do y, we'll put in terms of x, substitute over here, and we'll take the limits and we'll get the answer. This is generally how we approach. So as we have done earlier, we'll find the mass per unit volume, that is density, that is mass upon volume is equal to density, that is rho. So this is constant for a body. Then we find the volume of this small disk, which is nothing but a very small cylinder of radius y and thickness dx. So volume, differential element of volume, it comes out to be pi r square into h, where r is y and this is dx. So this is volume. So obviously mass, element of mass, differential element of mass, mass is equal to volume into density. Volume is what? Differential element of volume, pi y square into dx. This is volume into density is rho. So this is the differential element of mass. Then moment of inertia about this center of mass. So ICM for this disk about a diameter is, we know that is, it is mr square by 4, it is dm into r square is y square by 4. So this comes out to dm is what? Dm is pi y square dx into rho dm into y square by 4. So this is ICM of what? Of this general disk about this axis. Then we can use the parallax theorem, that is Iyy dash is equal to ycm plus dm into x square. So Iyy dash is integral of this whole term, that is this is ICM, mr square by 4 we have used over here, that is dm into r square by 4, ICM we have found it over here, plus dm into x square, parallax theorem. So now over here we have x also and we have y also. If we say, that is we intend to take limits from 0 to x is equal to r, if we intend to take the limits from here to here, then certainly we have to represent y in terms of x. Now what is that relationship between y and x? If you look over here, for any point, be it here, if this is x, this is y, but this will always remain as radius only. So we get y square plus x square is equal to r square. For any value of y, whether it is here or here, then x square plus y square will still be equal to r square only for this point also. So this is y square, we replace at r square minus x square. We put the value over here, we replace it over here, simple integration, and we get Iyy dash as 2 by 5 m r square, that is the moment of inertia of this solid hemisphere about this diameter. Interesting thing to note is, if we have, let's say, the whole sphere is there, solid sphere is there, and let's say this half makes of m1 and this is of some other material and it has a mass m2. So moment of inertia of this whole solid sphere is moment of inertia of this about this axis or plus of this about this axis, that is 2 by 5 m1 into r square plus 2 by 5 m2 into r square. The pattern will remain same. This about this axis. R square is same, 2 by 5 is common, we can take 2 by 5 r square, inside comes m1 plus m2, that is the total mass. So whatsoever the total mass of this, the moment of inertia of any solid sphere about diameter, the formula remains as 2 by 5 mr square, where m stands for the total mass of the sphere, r is the radius. So moment of inertia of this solid sphere about any diameter is 2 by 5 mr square.